So we describe the acidity of a proton in a functional group with pKa. And pKa comes from the equilibrium constant. So if you take any acid-base reaction like we have at the top, the K of equilibrium for this reaction is the products multiplied, the concentration of the products multiplied together divided by the concentration of the reactants. The thing is that H2O always has a constant concentration. It's like 55 molar. And so we have a new constant called Ka, which is just the equilibrium constant multiplied by the concentration of water. So we wind up with our new equation here, and that's the that's the Ka. And the pKa equation is just like the pH equation. It's the negative log of the Ka is the pKa. And so what that means is that strong acids, and strong acids are defined as having a pKa of less than 0. The strongest acids have these very low pKa's, which means that the reaction goes far to the product side. We have a lot of the conjugate base in solution. Whereas these weakest acids, and we're talking really weak, it's kind of absurd to really talk about them as acids, have these really high pKa values. And so there's a range. If you look at the list of functional groups here and their pKa's, you'll see that the carboxylic acid with 4.75 as its pKa is the most acidic of the organic compounds. But that's really not very acidic. That's still a Ka of 10 to the minus 4.75, about 10 to the minus 5 for the Ka, which means that you really have a lot of the starting material, the reactants, in solution and not very much of your products. Okay, so the way that we can use pKa for a couple of things. And one is to tell if a reaction is going to be spontaneous. And spontaneous means a couple of things. It means that it just happens. It releases energy. It means that the reactants are higher in energy than the products. And so, for instance, here we have acetic acid, and we look at the functional group, and we know from the previous table that the pKa is around 4.8. And then we can look at the conjugate acid, which would be phenol, pKa is 10. And as long as we're going from a stronger acid and base, so pKa 4.8, to a weaker, well, we really just look at the conjugate acid, a weaker conjugate acid, then the reaction is going to be spontaneous. The other thing that's really common to do is to use pKa's to figure out which proton in a molecule is most acidic. If you just look at the whole molecule, you don't have to look up every proton. Look at the heteroatoms and if there are any protons directly bonded to an oxygen. In this case, there's actually two functional groups, the carboxylic acid and the phenol over here, that do have protons directly bonded to an oxygen. But if you look up their pKa, the pKa of the carboxylic acid is lower than that of the phenol. And so you can see that the conjugate base is the one in which the carboxylic acid is deprotonated to give the carboxylate. It would be unlikely to deprotonate both of your of those protons. Do note that for this first test, you don't have to memorize any of the pKa's. You will get a pKa table. Finally, with pKa, we can use it to figure out basicity, but it's always a little mind-bending. So what we're looking at here is if the acid has a negative pKa, that means that the reaction has a Ka where more than 50%, where basically you get more products than you have reactants, and so this would be a strong acid. That leads to a stable conjugate base, which we'll talk more about in the next video. And since it's nice and stable, it's a weak base. And so if you have these very low pKa values, the conjugate base will be a weak base. Conversely, if you have a very high pKa value, the conjugate base is not stable at all. It's very high in energy, and so that is a strong base.